Okay, so good morning, dear audience. I'm Paula Fulaneto, and I am the current chapter president for UMass Inform, and I will be your host today. And this is our first talk for the Spring Speaker Series. It is a great pleasure that the UMass Amherst student chapter of Informs and its faculty, Dr. Anna Naguni, receive you today for the seminar of Dr. Ann Melissa Campbell. Dr. Campbell is Department Executive Officer of the Department of Business Analytics at the TP College of Business at the University of Iowa, where she is also the Clement and Sylvia Hansen Family Chair in Manufacturing Productivity. Dr. Campbell joined the University of Iowa after getting her PhD from the School of Industrial and Systems Engineering at Georgia Institute of Technology. Her research focus on freight transportation, especially on problems related to new and emerging business models. She works on problems related to inventory routing, consumer direct delivery, route planning using stochastic information, and logistics planning for disaster relief. She publishes in journals such as Transportation Science and Network. Last but not least, she's an NSF Career Award, and she serves as an area editor for Transportation Science. She also led her department efforts to win the 2021 Informs UPS George Smith Prize for Excellence in Analytics Education, and congratulations on that one.
Thank you.
We thank you, Dr. Campbell, for accepting your highly, as we can see, awarded speaker. And we are honored to have you here today. I'm going to pass to Dr. Naguni if she wants to say some more words.
Yes. Thank you very much. Thank you, audience. Thank you, Professor Campbell. We're very honored to have you kick off our 2022 speaker series. And also I want to announce that her talk has made the UMass homepage, along with the UMass hockey game and UMass basketball. So operations, research, management, science really rocks at UMass. So thank you. Thank you. Quite the achievement.
I will not be playing any hockey or basketball, so hopefully we can live up to that.
Thank you, and welcome
so
everyone.
Before we start, I'll ask you all to be muted, and if you feel like you want to keep your cameras off, go on. I'll ask you to put your cameras back on the end for our Q&As. I always feel it's better to talk to people than not just to black boxes. And also, please hold your questions until the end. We're going to have a Q&A in the end. And Dr. Campbell, please go on. The floor is all yours. Thank you very much.
Great. Thank you. Thank you, Paula. Thank you, Anna. I really appreciate being here. You guys are the best tweeters. Using word like rock star on Twitter today, I feel pretty intimidated to live up to that. But I will do my best in my way of talking about does parking matter in routing last mile deliveries. I will say I will give this presentation, and then at the end in the Q&A, I'm a pretty open book. So if there's anything you want to ask outside of research, career advice, choosing an advisor, whatever, I'm open to discussing anything. I've kind of been through most all of it at this point in my career. So the title of my talk, Does Parking Matter in Routing Last Mile Deliveries? It is joint work with Barry Thomas, who's also in the transportation research area, who's at the University of Iowa and in my department, and Sarah Reed, who was my PhD student, who is now an assistant professor at the University of Kansas. Our paper that I'll be presenting is in the second round at Transportation Science, so we have put it on archive if anyone would like access to it while it's in process. So before getting to the issue of parking, I want to go over what I mean by last mile deliveries in case that's not something everyone is familiar with as a term. So when we talk about last mile, we're talking about delivering packages to your home. So when you think about ordering something on Amazon, it may need to be shipped from one warehouse to your local warehouse before it gets on a van to come to your house. I am talking about just that last piece of the van taking it to your house. That's just one part of a company like Amazon's logistics challenge, and that's the piece that I'm going to be focusing on today. You may think that's just one sort of small piece of the whole puzzle, but there's a lot of challenging logistics problems related to just that last mile. And I would say even more so since the start of the COVID pandemic, because we're all ordering more and more online. I know I order a lot of things I used to buy at the grocery store and Target. I'm thinking you guys probably have some too. I order dog food and all of these things that have to now be delivered by Amazon, creating more demand for these limited drivers. So a lot of people are looking at ways to handle this last mile more efficiently. You've all seen people looking at drone technology, robots, crowd shipping. All of these are ways to sort of do and deal with that last mile. My group of Barry and Sarah, we were actually exploring the idea of using autonomous vehicles for the last mile when we started thinking about the parking part of last mile delivery. And we started realizing very little academic work really addresses the issue of the fact that the delivery drivers need to park. If you think about the TSP or traveling salesman problem, for example, they're just modeling the order that a driver would need to visit the customers, but it doesn't really incorporate the fact that depending on where the customer is, it may take quite a long time to park at certain locations. VRP is the same as well. And we were really surprised at sort of how little attention had been paid to parking when parking is very clearly a time-consuming part of a driver's day. You think about an Amazon driver, a UPS driver, they're making 50 to 100 stops every single day. And particularly in urban environments, that's a lot of parking that they're having to do. So to quantify what I mean by the parking time, we found this nice survey from INRIX that gives some average parking times at 10 different urban environments in the United States. Notice Iowa City, where I am, is not on the list. We're talking about bigger cities where we got 15 minutes to find each parking spot in New York City. And we're giving Seattle is in bold to represent the average. So 9 minutes every time you find a parking spot on street in the downtown Seattle area. So if you think about, again, 50 to 100 deliveries per day, these 9 minutes are really going to add up to be a significant portion of these drivers that are in high demand, the use of their day. If you're used to solving the TSP and are familiar with that, you may think this is just an inevitable thing, that we have to park at every spot. This is just an evil that exists. But when you really think about it, the parking decisions are strategic decisions. You could have, instead of parking everywhere, you could park at one location and accumulate several packages in your bag and walk to those customers, walk to those, make those deliveries on foot, and then come back to the parking location and drive again. We all know that happens. We all see that with our mailmen, our mail women, but we don't really see this addressed very formally in an academic environment. So one of the things we wanted to do was look at how companies like UPS and Amazon handle this parking issue. Of course, a lot of these are not completely forthcoming in exactly what they do. But to the best of our knowledge of digging around on the web, what it seems like companies like UPS do is give the drivers their route for the day in the form of a TSP solution. So what order makes sense in terms of distance. And then it's up to the driver to decide where they want to park and which customers they want to carry the packages and deliver on foot before returning to the parking place. So they're making these parking and walking decisions, but they're making them kind of dynamically rather than a priori in an optimization type decision. And obviously we can't imagine that that the driver is doing it in the optimal way, but probably doing it in a pretty good way. And what we have found in the literature is very little literature that precisely looks at the parking problem in the same way, at least, that we see it. The closest that we found was this paper here by Martinez Sikora et al. That was published in 2020, where they look at the idea that we have to partition customers into walking sets and that we have to choose a parking location within each set, okay? And so then the objective value is a combination of driving time and walking time, like exists in practice. But what you'll notice is they put a weight of alpha and 1 minus alpha on the walking and driving time rather than just add them up, when adding them up presents part of the time of the driver's tour. And what is missing in this objective is there's no value for the parking time. So it really made us question sort of how does including the actual time for parking impact the routing decisions? Is this appropriate, or should we specifically incorporate the amount of parking time in the decisions in our optimization? And if so, what kind of difference does it make? So to sort of motivate you to think about this, I'm going to give you a kind of fun, simple example. I'm going to ask you to put your answer in the chat when I ask you the question. We're going to start with this simple model of one way we can handle the parking, walking trade-off with 8 customers. So let's say we have a truck and a driver and they're at the depot and we want to serve 8 customers, okay? So we're going to leave the depot and go to the first customer out of the 8, and we're going to park. It's going to take however many minutes to park. And then we're going to assume the driver has the capacity to carry 4 packages in their bag. So the driver is going to walk around and deliver the 4 packages at the 4 sites in blue. Then when he or she is done, returns to the parking place, and they can get in the car and drive and drive over to the next set of 4, park, and get out and repeat this process, okay? So that's one way we can incorporate parking and walking, okay? But I want you to consider option 2, okay? Another thing I could do instead is park at the first customer, deliver those 4, but once the driver returns back to the vehicle, instead of driving, he or she could load 4 more packages in their bag and walk over and visit the other 4 customers in the service area before coming back to the vehicle and starting to drive. Can you think about any time that it would make sense to do this extra walking rather than get in the vehicle and drive over to this area? So I'm going to check in the chat. I want you to try to guess for me, when would it be better to walk this extra distance than get in the car and drive? Can anybody take a guess? Downtown Boston, okay. What's true about downtown Boston that it would make this true? Let everybody guess. When the parking time, yes. So everybody's sort of getting it. Parking, there's no parking, absolutely, okay? You guys are great, okay? So that's the issue, right? It might be worth it to walk the further distance when the time to get in my vehicle and park would take longer, right? So that gave us sort of evidence with a simple example that considering the parking time, the trade-off of the parking time versus the walking time is important to consider in the optimization and can affect the solutions. Okay. So the problem we then introduce considers these different factors. Okay, so the problem that we introduced to study is called the capacitated delivery problem with parking. We're starting with just considering a single vehicle with a single delivery person to keep everything clean and simple for starters. The key thing is the delivery person, every time they go deliver a set of packages, they can either come back to the parking spot and drive again, or they can reload and walk to a new area to deliver the packages. They have that option that we saw in option 2 a minute ago. We're going to assume that there is a loading time per package. So every package the driver collects and puts in their bag has a constant loading time. So that's not going to be a big factor. And the delivery person has a capacity queue. So that refers to the number of packages he or she can carry. We're going to assume each package for now uses the same amount of capacity, but obviously we could extend it to be pounds and so forth. But this just keeps it clear and simple to sort of see what's going on. So the strategic decisions in this CDPP are where to have the vehicle drive and park versus where to have the driver go walk with packages or walk back to the parking spot and reload and walk again. So there's these driving, parking, and walking decisions. And our goal is to minimize the completion time of the tour. Why do we want to do that? Because that minimizes the amount of time the driver is taking to make his or her deliveries, does the best use of capacity of the driver, which we again said at the beginning was our precious resource, because we're all ordering so many things online. We want to help them get this done as fast as possible. Okay. So we want to model this problem. I'm going to save you from a whole bunch of constraints and just talk about the objective, because the objective has the different decision variables that kind of make the problem challenging. And so I want to just talk about the objective and the variables that go into the objective. Not going to go into all of the constraints. Okay. So we have two different variables. We have an X and a Y. We essentially have a variable to represent driving and parking, and a variable Y to represent our choice of the customer service sets. So the customer service sets represents the group of customers that are served together from a particular parking spot. So one group at a time. So you may have multiple service sets served from the same parking spot if the driver comes back and reloads. So the objective function does kind of what you think it would do. The left-hand side represents the time spent driving and parking. So it reflects the cost associated with the X variable decisions. So that D parameter is going to reflect the time of driving plus the time of parking, because the observation to make is really all of the driving that's going to take place in the tour is to drive to a place that you're going to park, right? There's no point driving somewhere without parking, right? That's part of the sort of rules of the CDPP. The second part of the objective is the cost for getting out and serving the customers on foot. So the cost associated with our Y decisions. So every time we make a decision to park at a location I, then we're going to choose a set I, or excuse me, a set J to walk to from parking spot I, and we're going to walk to those. It costs W. And then there's a loading cost associated with putting all those packages in my bag. So the objective kind of handles the two sort of sets of costs, the driving and parking and the walking and loading. Okay. So to start understanding sort of what are the answers to this question, we wanted to start by starting with the simplest case of the problem. I would say the simplest case of the problem is when the CDPP has parking time of 0, okay? If you have a parking time of 0, then we just have this mix of driving time and the walking time. But why would you ever want to walk if the parking time is 0? If you always can drive faster than you can walk and there's no parking time, the solution to the simplest instance of the CDPP is the TSP, right? If there's no parking time, you want to just go to every customer in the shortest path and park at each of them because it costs you nothing and you can't do better than that. So we wanted to figure out sort of where is the line where parking time gets high enough that it starts to matter, where we start getting those things like we saw in the example at the beginning, where you would rather walk that long distance than park. Where does parking time start to be big enough to start matter and changing the solution from the TSP? When does the structure of the problem change? So we started with some nice analytical results. We're able to prove the properties of the problem for when the parking time starts to matter on a complete grid. So if you remember, a complete grid is a grid with a customer at every grid point. And we're able to prove for when the capacity of the driver is 2, that we can set a bound on where the parking time, the minimum parking time for the TSP to no longer be the optimal solution, where it's worth solving the CDPP to get something different. And for Q equals 3, we can create even a different bound for that. I think this 2 times the time to walk a block, those kinds of things are a little hard to understand as they are. So I'm going to translate it into a graph where we've used realistic walking and driving times to turn that result into minutes. Okay, so what we find is that when Q equals 3, so that's when the driver can carry 3 packages at a time, which is a pretty normal amount as seen in some documented cases in London. So we use that a lot as our benchmark. That when parking is 1 minute or more, 1 minute or more, the optimal solution to the CDPP is no longer the TSP solution. Meaning if parking is more than 1 minute, it starts to become worthwhile to change the solution, not park everywhere, and start changing the solution structure away from the TSPP. Do we think the parking time in an urban environment is likely to be higher than 1 minute? Yes, right? We saw lots of numbers at the beginning, 9 minutes, 15 minutes. So very likely in an urban environment that when we solve the CDPP, we're going to get solutions quite different from the TSP, with only a minimum of parking time of 1. Okay, so let's go over to the right-hand side, which represents rural environments. So think of country areas where houses are more spread out. If we look at the appropriate parameters for there, we need parking time to be at least 4 minutes for the CDPP to have different solutions than the TSPP, than the TSP. Do we think in rural situations the parking times are probably more than 4 minutes? Probably not. Maybe some places there are. So our conclusion is sort of it's less likely that we really need to solve the CDPP instead of the TSP in rural environments. So conclusion of sort of this first part, I kind of said it, but I want to just kind of drill it in, that we can get productivity gains in urban environments by considering the search time for parking. So if we want to minimize the driver's day, we're going to get different solutions and better solutions by considering the parking time in urban environments. Okay, so that's sort of our theme 1. All right. So now we want to be able to solve this problem more generally. So not just on a solid grid. We want to be able to solve big enough instances that we can start to get an idea of solutions, see where we park, where we walk, start being able to solve them. And let's point out one of the barriers to being able to solve this problem. Okay, I sort of highlighted in yellow is we have these sets, J, that represents every grouping of customers that we may want to walk to from a particular parking spot. So if we have Q equals to 3, meaning a capacity of 3, this will be all sets of size 3, 2, and 1, right? So this is quickly going to explode and be a very big number. So that's what creates sort of the challenge to the problem, is the number of those sets and thus the number of Y variables that we need to choose from those sets. So the obvious place to look for improvement is looking for ways to try to cut down some of those sets J. So we tried a lot of different ideas. Some things that seem intuitively true, can't really prove, like you would think you wouldn't want to set with a customer up here and up here, but it is really hard to say never on a lot of the potential sets. But what we could figure out as a way to simplify the sets is we could sort of decompose the sets to reduce the options a little bit, or we could get solutions where we just group singleton sets for the sets where the driver parks and serves just that one customer, and then the ones that the driver serves on foot after the one where he parks or he or she parks, that can be a separate kind of set. So we kind of came up with parking sets and walking only sets, and that helped us reduce our set sizes to be able to solve instances with 50 customers. That was sort of our goal, as we thought we needed 50 customers to be able to sort of get realistic instance sizes for our experiments. So we came up with this, we came up with some valid inequalities, and the composition of things we were able to do, get it where we could solve instances of size 50 customers within just a couple hours. And so that was our goal. But I admit now, and I'll mention later, there's definitely more that could be done there, but that's where we wanted to get to be able to get to start solving the problem and really see what happens. I'm always eager to see what happens. Okay, so now I want to talk about how we can see what happens. So we want to solve the CDPP, but we want to understand its value. And remember, we want to see what's the value in saving the driver's time. How much are we saving the driver's time? So we need benchmarks for comparison. So the first benchmark we're going to use for comparison is that one I brought up before, which is we're going to solve the CDPP with P equals to 0, right? So ignoring parking time, see what the solution is going to be. We know it's going to be one where we park a lot of places, and then we're going to add back in the actual parking time so we can get an idea of what that solution would have cost us with a real parking time. So we're going to take the solution and add in a parking time to get what the realization of this CDPP solution would be. Okay. Then we're going to try to do our best job to represent what happens in practice. We told you that, to the best of our knowledge, Amazon and UPS give drivers a TSP tour. So we're going to assume that we're going to follow the order of the TSP solution, but given that order, optimally decide where to park and where to walk. So we're going to be the sort of world's smartest UPS or Amazon driver in making those decisions of how they should execute the TSP tour. So we're giving our best sort of benchmark for an in-practice solution. And then the third and final benchmark is we want to implement that Martinez-Sikora solution from the beginning. If you remember, they had walking and driving and their objective function with that alpha factor that we have to choose, but it ignored the parking time and the objective. So we want to see, if we use these options, how would the completion time of the driver's tour be different than if we solved the CDPP as we defined it? Okay, so we want to be able to do sort of a good set of tests to really build some insight of where it really matters. So I think this is a little funny. We wanted to represent urban, suburban, and rural counties. So we wanted to pull data about urban, rural, and suburban counties. So we looked at the USDA urban to rural continuum, and they label all counties from 1 to 9 as being more rural and more urban. And so we took a county of sort of the different extremes, sort of at the most urban, and the middle more suburban and rural. Why I think it's funny is because Iowa didn't have one of the most urban counties. So we went over to our neighbor in Illinois, where Cook County includes Chicago. Adams is a suburban, and Cumberland represents a rural county. So we want to use those for our tests and be able to pull instances of size 50 from those counties. And then we had to make some assumptions about parking times, because we don't obviously know in Adams County in Illinois how long on average it takes to park. So we just tried to give it a reasonable guess, where with the urban, we went with the 9 minutes that we saw in Seattle. In the suburban, we went in the middle with 5 minutes. In the rural, we went with the very low 1 minute to park, right? Because we assume in a rural location, there's not a lot of hunting for parking spots. For the capacity of the delivery person, we set it equal to 3. As I mentioned earlier, we found that in a study of London, as well as the loading time per package was found to be 2.1 in the study in London. We're just trying to be as reasonable and fair as we could for our experiments. When we run the experiments and compare it with the benchmark, this is what we get for the urban, suburban, and rural counties. So what you're seeing in the percentages is the percent larger in the driver's tour for using these different benchmarks, okay? So let's start on the right with the rural county. So we see with the different benchmarks, we get as high as 6% longer tours if we use something other than the CDPP. That's not too bad. So I would say the conclusion we can reach here is solving the CDPP is not that valuable in rural environments. We kind of thought that earlier from our analytical study, but even with these practical instances, we're sort of seeing it again, okay? But let's look in the middle in the suburbs. What we see there is for a lot of our benchmarks, the tours are 29–28% longer than solving the CDPP. So we're still getting a lot of savings from solving the CDPP. And the biggest one is for the urban environment, which is what we expected. With a P equals 9, the tours become 50, 48, 11% longer if we don't solve them with the CDPP. So even though the 11 is way better than 53, still a company like UPS or Amazon is very interested in solving 11% on the length of a driver's tour. So it's still promising to really consider parking in the optimization. Okay, so this one I think is interesting because in the paper, besides being able to solve with the benchmarks, we wanted to see an experiment with different parameters. One of the parameters that's interesting to experiment with is the capacity of the driver. So with Q equals 1, we're saying the driver can only hold 1 package at a time. With Q equals 4, he or she can carry 4 packages at a time. So there's more that they can go serve in one walking trip, okay? What I think is interesting here is in the most rural county, you don't really see much difference at all, allowing up to 4 packages to be carried. Is that surprising? Not really, because in a rural environment, he or she is probably going to only carry 1 package at a time because they're driving everywhere, parking everywhere, and getting out with just 1 package. So not a lot of savings from being able to walk and carry 4 packages. But as we go to more suburban and then more urban environments, we start to see a real nice improvement from being able to carry a larger number of packages, right? So you can think about here, we're getting our best delivery time with Q equal 4, because this means there's a lot of instances in an urban environment where it's desirable for the driver to carry 4 on foot before coming back to the parking spot. So it gives you another idea of way we can reduce the day for the driver. And then what I think is most interesting, that'll take just a minute to kind of understand, is looking at how the driver's day is spent if we break it up across the different activities they do in a day. So we're going to have yellow represents parking time. The gray represents walking time. Okay, so when P equals 0, so when the driver does not have to take any time to park, there's no parking time, thus no yellow. And he or she can be done with her day in 130 minutes in this example. Okay, as we go to larger parking times, this is what we get as the times of the tour: 225, 255, and 272 minutes. But what's interesting is if you look at it, this is the parking time, 47, 40, 47, not much different, but what changes is the walking time. That shows us that how the driver is using their time to walk to more places, go back to the parking spot and reload and walk further, like we saw in that early example, is really happening. Okay, so I mentioned before that the problem kind of blows up, right? Because we have to create those sets for all the potential groups of customers we're going to walk to. So we have created a nice heuristic for being able to solve those larger instances. It's really a two-phase heuristic, where the first phase is very much like what we call a location problem, where instead of locating hubs, we're locating parking spots. And instead of allocating customers to hubs, we're allocating customers to parking spots. So it's kind of a hub allocation in the first phase. And the second phase, we're then figuring out the more detailed routing solutions. So when we do that, we find that our heuristic tends to work quite well. When we compare it with problems we can get the optimal solution for, we're able to get solutions within 1.6, 1.5, up to 5% of optimality. And they're still quite a lot better than those benchmarks I showed you earlier. So they're not quite as good as the optimal CDPP, but they still are a lot more successful than the benchmarks. So it's promising. I think that's an opportunity for more work as well. Okay. So big conclusion, parking does matter. Hopefully you got that. I kind of drove it home a lot. Particularly, I would say in urban and suburban environments, really incorporating the parking in your optimization can really yield tours that are shorter for our drivers. Outside of rural environments, we showed that the larger capacity the driver has for carrying packages, it can start to really make a difference on the completion times of the tour. We also saw that the longer search times for parking changes the structure of the solution. So that's when I showed you, you walk more, you reload more, as the parking time gets bigger, as a way to avoid having to park more times and increase that parking cost further. And then our last is that we did establish a heuristic that finds high quality solutions for these very difficult problems, often in less than a minute. So we're pretty happy with that and hope people continue to work on that. But what I really sort of want to talk about a little bit, and happy to answer any questions about, is what's next. I really want to emphasize, and I put it sort of at the bottom, and you're welcome to take and steal, is that I think considering parking is a very rich research area. And I think a lot of people should consider it because it's such a real world problem. Everybody relates to it, but so few papers really address it in a careful, thoughtful way. So some of the things that are open and are things we'll consider, but are open to sharing, are looking at exploring the impact of different parking location options. So for example, in our paper, we considered only parking at the customer locations, but it may be that some customers don't have parking and some do. But what I think is more interesting is some cities are considering experimenting with parking areas for delivery trucks and making sort of parking zones. And you could really explore how these innovations could improve or not improve the drive time for drivers. And you could really explore that in a way to help cities understand what's really a good idea and what's not. I also think one of the issues we didn't address, but is obviously a big one, is this problem is very time dependent. Obviously, New York City, the parking time, or Boston or Seattle or any of those, certain times of the day are going to have worse parking times than others. Likewise, the geography, even within a downtown, might be certain parts of downtown are going to have higher parking times than others, even at the same time of day. So there's a lot of things that we can even get to put a finer grain on the parking times. Again, we're just starting with sort of a initial look, but there's a lot more that could be done in that space. One of the things we're working on now, as I mentioned earlier, I like to look at stochastic versions of the problem. I think one of the things we did here is we just assumed parking at the customer would take 9 minutes or 6 minutes. But it may be in reality that in 9 minutes, you're cruising around looking for a spot and maybe you find one at the customer, maybe it's down the road. So we're also looking at strategies for drivers of like when they find a spot available, when should they take it versus when should they keep cruising. I like the idea of drivers cruising. It sounds like way more fun than it actually is. But I really think parking is a really rich area, and I think it's something that there's a lot more that could be done. And that concludes my presentation. I already appreciate Anna for mentioning the 2021 UPS George C. Smith Prize. It is a prize we're very happy and proud of to win. It was my first job as department head was to apply for that. So once we got it, I think everybody's expectations maybe got a little too high in the department. But I would appreciate any questions now, but you're also welcome to reach out to me anytime by email. I'm on Twitter and try to put my new papers out on Twitter. So that's another way to connect with me. All right, Paula.
Thank you so much. That was so interesting. Before we move on, I just wanted to ask everybody if they could take their cameras off so we can do our virtual picture, because somebody may need to run earlier and I would like to get as many of our faces as we could. So if you feel like, please do the Zoom version of our group picture. Good to go. Thank you. Okay, with that, I just wanted to thank you. This talk was great. I always find it interesting when you listen to a topic that is not on your area and it makes you think of your like crazy. I have full set of notes, but before that, I'm going to open the Q&A for other people. And if they don't have questions, I do have quite a bit. Thank you very much. That was very informative.
First applause.
And so if you want to talk, feel free to raise your hand or to type it on the chat, and we'll follow suit. So I see Professor Sloak has a question. Please go on.
And I think you have a question too.
Yes. Okay, let Professor Solek go first.
Okay, thank you. Well, thanks, and I mean, it certainly was, a very valuable research work that you presented. It was very informative, as Paula mentioned. I just had one observation, and actually wanted to see its impact on the application. So what I see, especially in big cities, is that when drivers cannot find a legal parking spot, they would actually just stay on the road blocking traffic, or maybe not even blocking it, but at least illegally being there. And that obviously might be reducing the parking times in urban environments. I don't know how much of an impact it would have in this type of a setting, whether it implies that these findings are maybe upper bounds in terms of the value that it's being created, or just wanted to learn more about that application.
Sure, that's a great question. That's one we got in the first round of reviewers, so very fair question. The way we address that is illegal to just park in the middle of the road. So our model is based on we're going to follow the legal procedure. But that is why we put in the benchmark for P = 0, was to see what happens if you kind of ignore that. And we did more with that in the paper that I didn't go into here, because the reviewers wanted us to look at that question. There are some related papers that look at, you know, the amount of fines those kind of companies are doing and comparing that to the costs, but yeah, we assumed legal behavior, but because of that, we did explore some things with that and figuring out how much parking time it takes to make a difference and stuff like that. And maybe they do some cruising and then give up and do illegal parking. I think there's a lot of behavior things, yeah, that it's hard to model, but I completely agree that that's something people sometimes do, right?
Yeah, exactly. Thanks, Sam.
Sure.
Thank you. That was fascinating. It was so clear and such an important problem, and I love the presentation. So really appreciate it. I have several comments and questions. I remember a few years ago, I had a group of students do a project, but it was from traffic network equilibrium perspective on parking equilibrium. Because if you notice in various university parking lots, really professors and staff tend to park in the very same place, which I thought was really interesting. Okay, so that's one thing.
And there is some work on that's several years old, where they look at sort of strategies for looking at your parking spot in the parking lot.
Right.
And so that was exactly the basis for what we're looking at for cruising around blocks in a neighborhood. That's where we started from.
I was wondering if you've looked at maybe comparing the daytime kinds of parking issues versus nighttime. You probably know Jose Holguin-Viras of RPI, because he's done a lot of work for New York City on freight delivery vehicles, you know, coming at night, and what are the potential costs and also the time savings. But obviously you have to pay the people, you know, to offload and unload. You know, there's safety issues at night too, because of maybe enhanced crime and so on. But I think that would be really interesting. Maybe that'd be more empirical though, I don't know.
Well, you could do something like, well, obviously the parking time will be less at night. So maybe you could complete the driver's day faster at night, but maybe you have to pay them more. So there might be some interesting trade-offs to look at that way. I'm not sure how it models a safety issue other than you'd have to pay them more. Would be an interesting way to look at the mix.
And the thing is, like, congestion isn't factored in at all in terms of the TSP, right? In urban areas like Boston or New York, it's still linear.
Right, and it's just sort of assuming maybe a slower speed and a higher parking time. Yeah.
Okay, thank you.
Sure. Students, who's going to now study parking?
Right. Oh, I think so. I started hashtagging parking matters. And also there are apps for finding parking. I know in Boston.
Yes, in Chicago.
Right. So I wonder how that could be. Yeah. Really
I think that's kind of an interesting piece too, is when you get to sort of that strategic, or we just like assumed you parked at the customer and it took this fixed amount of time. Maybe you could use one of those apps in Chicago and it could tell you where you could park. And those tell you where to park, but then you still have to decide which of those spots you want to take, right? And how far away it is. And so I think there's still a lot there to consider. Even with making it less stochastic, you still have that decision to make. But I hope
you can come to Jack Levis's talk and quiz him. UPS. That would be really great. Discussion.
Maybe not. Maybe I'll ask it real nice.
Offline.
Yeah. Hi. First of all, thank you so much for this interesting talk. It's very different from what I do, so I found it very fascinating. I wanted to ask, because you work in this field, so you may know, I have just read in the news or, corners and fringe of the new things coming up. So given that all this, urban planning, smart urban planning, in that regard, aren't cities and communities and organizations partnering to have dedicated areas? Because the new thing is everybody's going to rely on Amazon. These are things that are going to happen in all the retail settings, commercial settings, residential settings. So in that case, is it like because that's too far that there is value to helping them solve this problem, whereas it could be that smart city design can alleviate this issue from a different angle?
Right, so that's sort of what I was trying to allude to with the sort of future work slide is I don't think there's conventional wisdom yet on what that smart city parking design should look like, right? Some are looking at reserving spots at corners, some are looking at larger zone areas, there's all different schools of cities trying different things in different countries and different cities. And so being able to take something like a specific idea, put it in this model to limit the parking spots, you could really evaluate and compare how different strategies would affect a driver's day who serves a particular neighborhood. So I think something like this, if you extended it, you could use it as a vehicle to explore different strategies, right? So you could say maybe there's this parking zone that would make the parking time be very quick, but it would add a walking time of this. And so I think there's a way that we could use it to look at policy decisions, or one of your students could. That's why I'm maybe a weird advocate of parking now, because I think there's so much we could look at, because I do agree with you. It is such a wave of the future issue people are trying to solve. And as we go towards autonomous vehicles, which I said at the beginning was kind of how I got in here, we still need a way for autonomous vehicles to drop you off, right? Even if we have them. And so people are looking at drop-off zones for that, which may be the same as Amazon. So I think there's a lot in that direction. So thanks for the question.
Thank you for your answer. One more comment, which is probably coming like a reviewer kind of comment, but I wanted to ask that have you maybe already considered in your paper things like, because you're starting from that van has been packed with stuff, but could there be also optimization on what kind of packages you pack, because they might be walk friendly versus drive friendly? Is that something that maybe it's already there or it can be incorporated?
Yeah, I guess I would say we're inherently assuming everything in the van is something a driver could carry.
Okay.
But you're right, that is an issue. I don't know if there's an article about Amazon's optimization that came out a couple months ago that got a lot of publicity, that it talked about Amazon was recommending routes where a driver had to cross a highway carrying a big bag of dog food. So there's a lot of opportunities to consider all of those different things. Yeah, you're absolutely right.
Thank you for your input.
And there also maybe it's, some people are looking at carts and things for the drivers. I just use the example of the bag, but there may be other ways to do that.
I'm going to jump in because a lot of my remarks are connected to what Professor Aurora managed. I am on the industrial OR, public planning and energy sector of the UMass. So I was not expecting to be so interested when I talk about transportation. On my research perspective, itself is interesting, but you got me thinking on a bunch of things. The first one, Professor already talked about the city planning and how that kind of model, which might be a long optimization model, may really be interested to be run once in a while by the city planners, not necessarily by the people delivering. And because in my work, I look a little into emissions and into recharging of AVs. I was also thinking in a city that is using internal combustion engines, you could actually plug that into your experiment. The amount of times you turn on, because the emissions of turning on sometimes can be higher, you could count how much emissions you're saving by doing less startups. If you put on an EV, then you kill that problem, but now you need to charge that EV eventually. And if you start less, you have less pulse on your batteries, you charge less, you even kill it less, because driving is much better than startups. So actually there is a huge area of research for public planning and policy just by saying parking and the mass and enforcing. And then I was thinking of something that Professor Jay Taneja does, that is view of the cities with drones and satellites, kind of like integrating the idea of where you should park, how you should do it. And last but not least, you could even be teaching health for your employees. Instead of just driving, we're going to suggest that you do a little of the walking. Maybe we could be at the end of the month showing the best walkers of Amazon and be promoting walking.
Which is funny because
there's so much public policy out of parking that I'm like, I'm joining the hashtag. Like,
so Paul is my new co-author, just so you know, I've claimed her. It's funny you mentioned the health, because when one of my grad students heard this talk from Sarah, he was like, ooh, that may be too much walking. He was afraid we were going to end up having people have to walk too much in the cold. So there's all kinds of pieces to think about. I do think
that Walker City, so compared to the Midwest, we're more used to that. That might be also a way of like,
or at least balancing it. Maybe you can only do so much.
The older drivers may don't go in a very walkable area. Like you could actually optimize your fleet of employees. People who want to be more active could pick those ones. It's like there is a lot of ways of actually working flexibility. And
I think working in the electric, how long it make your electric charge go is interesting. I hadn't thought about that. But I don't know if you noticed, did you see the news recently about the contract for the new US mail vans that they just ordered, you know, what is it, millions or billions of dollars worth of vans, and they ordered all gas powered ones again. And it just, it's crazy to me that that didn't go through some sort of review. What did you say?
You can at least turn on, then that's why I gave you both sides. You can at least do the math on how much pollution you're saving, because it's pollution in thickly settled areas that matter. That stuff, that particulate matter that my kids are breathing, that you're breathing. So like you even have a collective pitch on that. So it's like, there is so much that can be done. Like I was impressed with how it connected to my area.
Cool, well, thank you. Well, reach out if you want to chat.
Thank you, thank you.
All right, any other questions?
Very stimulating discussion, fantastic.
All right, well, it's nice to be here. I've enjoyed seeing everyone this morning.
Thank you very much. And I'll follow up with a formal thank you letter and ask you, you know, how high up should I go to the governor of Iowa thanking you? All the legislators.
I haven't tried that yet.
I mean, I've done things like that. I'm fearless, so.
Well,
but it was really fascinating.
You have to teach me how to be fearless. I want to do that. I'm trying.
Really, really good. Thank you so much.
Everyone, Mona, it's good to see you in person. Or someone.
All the best.
Thank you. Yes.
Thank you, everyone.
Thank you for the talk. I really enjoyed it.
Bye bye.
So much.
Have a good holiday, everybody.
Yeah, long
Oh,
weekend.
President's Day. I was like, what holiday are we?
Monday, yeah. Monday is an extended weekend. You can do extra research, no classes.
I like your attitude.
All right, bye.
Bye-bye. Thank you again.
Bye bye.